So we've just defined the signed area of an oriented triangle. That's great. But now we're going to do something in addition to that. Something which is maybe a little bit curious. Something that maybe you don't see in a typical calculus course. We are going to define the signed area of an actual oriented side of just a segment which is oriented. So here's the definition. For an oriented side AB, its signed area is S of AB. And by definition, that's S of OAB, the oriented triangle OAB, where O is, of course, the origin. And we've just seen that that can be expressed in terms of a cross product if we want as 1/2 of OA cross OB. So here is a point A, here's a point B. Here is the segment AB, or the oriented side AB. Actually, officially, an oriented side is just a list or an ordered set of the 2 points, A, comma, B. That's officially what it is. But we write it down pictorially in terms of this segment with an arrow in the middle of it. Okay? That is the oriented side AB. It's like a line segment, but it has a direction, a start and an end. Okay, we are now going to define the signed area of this segment. And the definition is, it's the signed area of OAB. This oriented triangle, where O is the origin, that's an oriented triangle, it has a signed area. The signed area is 1/2 of the vector A cross the vector B. So just in terms of the vector little a and the vector little b, which are the sort of coordinate vectors of the points A and B, in other words, the vectors emanating from the origin to the point A and to the point B, then we could write just S of AB is 1/2 of A cross B. And let's note that if we interchange the orientation of the oriented side, S of BA, that's going to be minus S of AB, because that would just amount to interchanging the order of the two vectors in the cross product, which would just introduce a minus sign. So this is an intriguing kind of thing that we're doing here. Maybe not obvious why we would want to introduce the signed area of actually a side. And it sort of has to do with the position of the origin. So if the side is far away, then maybe the triangle has a relatively bigger area. If the side is closer, then maybe it has a relatively small area. So it's not just a question of the shape of the side, it's also where it is that's going to impact on the signed area of that side. So the importance of that notion becomes clear with this following theorem, the triangle signed area theorem. It is that for any oriented triangle ABC, the signed area of ABC, S of ABC, is equal to S of AB plus S of BC plus S of CA. The signed area of the oriented triangle, ABC, which is sort of represented by that red area, is actually the sum of three signed areas of its three oriented sides. So AB there would give us a triangle OAB. So this first thing here really corresponds to the signed area of that triangle there. And this one here, S of BC, corresponds to the signed area of the triangle BCO. So that's that triangle there. And this third one, S of CA, corresponds to the oriented triangle CAO. Okay, so that's that oriented triangle there. So the geometrical content is that if you want to calculate this area here, this signed area of ABC, that oriented triangle, then you can do it by taking the area here of OAB, adding the area of OBC, and then the area of OCA. And what happens here is that the orientation of these three triangles, determined by the three oriented sides, has some cancellation. That this oriented triangle here, the OCA one, that area will end up canceling with the contribution of the areas from the original ones in these portions here. So we end up getting this big area plus this big area, essentially sort of minus this big area in terms of absolute values. But that's not really the best way to think about it, just a signed area concept. It doesn't matter which ones are positive and which ones are negative. Okay, so let's prove this. And we'll do that by introducing coordinate vectors for our 3 points A, B, and C. So let's let OA be the vector A, OB be the vector little b, and OC be the vector little c. Okay, so then what is the signed area of ABC, which is on the left-hand side here? Well, by definition, it's 1/2 of AB cross AC. And what is AB? It's the vector from here to here. And in terms of this vector A and this vector B, it's B minus A. That's what AB is. Cross AC, here's AC. From here to here, in terms of the vectors A and C, this is vector C minus vector A, C minus A. Okay, and now we're going to use the distributive property of the linear aspect of the cross product. In this calculation here, there's really 4 terms. There's a B cross C, there's a minus B cross A, there's a minus A cross C, and there's a plus A cross A. And we know by now that an A cross A is going to be 0, so there's no need even to write that down. And now we're going to rearrange things because the minus B cross A can be rewritten as A cross B. To interchange the order, we introduce a minus sign. And the minus A cross C can be written as C cross A. So these 3 things become A cross B plus B cross C plus C cross A. And that's exactly what's appearing on the right-hand side here. 1/2 of A cross B is S of AB. 1/2 of B cross C is S of BC. And 1/2 of C cross A is S of CA. So proof of the triangle signed area theorem that allows us to rethink the area of a oriented triangle ABC in terms of the signed areas of the 3 oriented sides, AB, BC, and CA. This technology is actually very useful. It's very useful to be able to calculate the area of a triangle from knowing its 3 coordinate points. So let's have a look at an example. Here's a triangle ABC. A is the point 2, 1, B is the point 1, 4, C is the point 3, 3. And we're interested in the area of that triangle. Let's actually color it so we can see what we're talking about. So that's the triangle that we're interested in. And we have oriented the triangle ABC. So we want the signed area of that oriented triangle. Okay, so what's the definition of S of ABC? Well, it's 1/2 of AB cross AC. AB cross AC. So we take A to the next one in the order, cross A to the previous one in the order. All right, what are these vectors between the points? Between the point A and B, we have to take the difference in coordinates. Okay, so this is 1 minus 2, that's a minus 1, and 4 minus 1 is 3. That's the vector AB. And about the vector AC, we have to take the difference between these 2 coordinate points. 3 minus 2 is 1, and 3 minus 1 is 2. So the formula for the signed area is take the cross product of these 2 vectors. That's minus 1 times 2, minus 3 times 1, so that's minus 5. We have to divide by 2. We get minus 5 over 2. Great. Okay, that's cool. But now let's illustrate how it would work if we looked at the other side of the previous theorem. Let's look at the signed areas of the 3 oriented sides. Let's look at AB first. Okay. So with AB, the oriented triangle OAB, we calculate its signed area just by taking the cross product of the vector here times the vector there, and dividing by 2. So those vectors are just the coordinate vectors associated to the points A and B. So this vector here, emanating from the origin to A, will just be the vector 2, 1. And the vector OB will be 1, 4. So the oriented side AB has signed area 1/2 of 2, 1 cross 1, 4. And that's 2 times 4 minus 1 times 1. That's a 7 over 2 altogether. So that's the signed area of the oriented side AB. And what about the oriented side BC? Well, there we have to take the vectors B and C here. So basically the coordinate vectors of these things, which is 1, 4, 3, 3. Okay, so the cross product there is 1 times 3 minus 3 times 4. That's minus 9 all over 2. And finally, CA, we have to take these points and their associated coordinate vectors, 3, 3 cross 2, 1. And that's equal to the cross product 3 times 1 minus 3 times 2. That's minus 3 divided by 2. So you can see that we're doing something a little bit different than we were doing here. Here we had to find differences between points. Okay? Here we're just relying on the actual coordinates themselves. But admittedly, we have to do more work. Do 3 of them. Okay, when we add up all of these signed areas of the oriented sides, what do we get? We get 7/2 for S of AB, minus 9 over 2 for S of BC, minus 3 over 2 for S of CA, and that totals minus 5 over 2. So we do get the same answer as in the original calculation. So that triangle signed area theorem that we just talked about has an immediate consequence of a famous formula that's usually associated to linear algebra. It's a formula for the area, or in fact the signed area of a triangle in terms of actually the coordinate points. So suppose that we have a triangle. Now we'll change notation a little bit. We'll call it A1, A2, A3, and the points will be general points. So A1 is x1, y1, A2 is x2, y2, and A3 is x3, y3. And we're interested in the signed area of the oriented triangle A1, A2, A3. Okay, and here's the formula. Its numerator is a little bit complicated. It has these 6 terms. x1, y2 minus y1, x2. Well, that's just the cross product of the associated vectors here. x1, y2 minus y1, x2. And then the next term is x2, y3 minus y2, x3. Well, that's just the cross product of the associated vectors here. x2, y3 minus y2, x3. Plus x3, y1 minus y3, x1. Well, that's just the cross product of the associated vectors between this one and this one. Namely, x3, y1 minus y3, x1. And all of that divided by 2. So the proof is immediate from the triangle signed area theorem. This is just a restating of that in the special case when we actually know what the 3 points are. And these ingredients here are just the various signed areas of the oriented sides of the triangle. So a natural question is, can we now extend this notion of signed areas to more general figures? For example, to quadrilaterals, or maybe to more general-oriented n-gons. Here is a quadrilateral, 4 points, A1, A2, A3, A4, and there's a specific order that we're going in, going around this direction here, so it becomes oriented in the same way that an oriented triangle is oriented. And it's represented by this little circle here that sort of represents the orientation, and that's obvious terminology that we could use to represent such an oriented quadrilateral. And the natural question is, can we have a theory of signed areas for these things? Can we get sort of corresponding formulas? So let's investigate this question about how we should approach the idea of signed area of an oriented fourgon, let's say. This one here, A1, A2, A3, A4. And an obvious thing to do is to say, well, why don't we decompose this into triangles, because we know the signed areas for triangles. All right, so let's pick some point B. In this case, in the interior of this quadrilateral. And then we see that by joining B to the 4 points, we get 4 triangles. And the orientation that we're assuming on the original quadrilateral, A1, A2, A3, A4, automatically induces orientations on each of these subtriangles. Okay? Because implicit in this orientation is the fact that this side is oriented this way. But if this side is oriented this way, then that's consistent with an orientation in this direction of this triangle. Similarly, the orientation of this side gives an orientation of this triangle like this. The orientation here gives us an orientation like this. And the orientation here gives us an orientation like this. So each of these subtriangles is actually a oriented triangle, which is good because then we can take its signed area. So a logical progression would be that if the signed area of the quadrangle is defined, it ought to have the following formula. It ought to be that this signed area is the sum of the signed areas of the four constituent triangles, namely A1, A2B, and A2, A3B, and A3, A4B, and A4, A1B. Okay, so let's investigate what that would mean. Because we know that each one of these oriented triangles can be further reduced into a sum of three oriented sides, or signed areas of oriented sides. So for example, A1, A2B, this triangle here, A1, A2B, its signed area is actually the sum of the three signed areas of its oriented sides, namely S of A1, A2, S of A2B, and S of BA1. Similarly, the next one, A2, A3B, is a sum of its three signed areas of oriented sides, namely S of A2, A3, plus S of A3B, plus S of BA2. And then the next one, which is S of A3, A4B, there it is there. It's the sum of, this line here, S of A3, A4, S of A4B, and S of BA3. And finally, the last ingredient, the triangle A4, A1B, its signed area is S of A4, A1, plus S of A1B, plus S of BA4. Okay, so we have these 12 terms altogether. And now we sit back and just have a look at them. And I think you can probably guess what's going to happen. There's going to be cancellation. So this S of A2B, have a look at that one and this one. Here's an S of BA2. These oriented sides are exactly opposite, so they're going to have negative signed areas. The signed area of this plus the signed area of this is going to cancel. This S of BA1 is going to cancel with this S of A1B. Those are going to cancel. The S of A3B is going to cancel with S of BA3. And the S of A4B is going to cancel with the S of BA4. So all of these 8 terms are going to cancel in pairs. And what's left is just these first 4 entries. S of A1, A2, plus S of A2, A3, plus S of A3, A4, plus S of A4, A1. So in other words, if we have a notion of signed areas of oriented quadrilaterals, then S of A1, A2, A3, A4 ought to be the sum of the signed areas of its 4 oriented sides. S of A1, A2, plus S of A2, A3, plus S of A3, A4, plus S of A4, A1. That ought to be correct. And notice that at this stage here, the point B has vanished. There's no more reference to the point B. That means that effectively we've discovered a way of pinning down what this quantity actually is. We can then define this thing in terms of the sum of these 4 signed areas of its oriented sides. Okay? Very important that we're first proceeding by thinking about what the definition of the signed area of the region in question is. I'm not assuming that we know that. We have to pin down what that signed area is, and here we have pinned down a very good potential choice for what the definition of the signed area of a quadrilateral might be. Okay, so that analysis leads us to the following definition. It's a definition of the signed area of an oriented fourgon. Fourgon A1, A2, A3, A4, and it's an oriented fourgon or quadrilateral. And the definition is that this signed area is going to be, just as we said, the sum of the signed areas of its four oriented sides. S of A1, A2 plus S of A2, A3 plus S of A3, A4 plus S of A4, A1, closing the circle and coming back to where we started. So A1, A2, A3, A4, in this case an orientation in this direction, fine. Then we have these four oriented sides. There they are there. Then if we include the origin here, then we have these four oriented triangles, each one corresponding to a side, as well as this one here. But this one here will actually have this orientation. And when we add up the signed area of this, plus the signed area of this, plus the signed area of this, plus the signed area of this, then we get what's a reasonable notion for the signed area of the quadrilateral. And so now we can rewrite that in terms of Meister's formula. So Meister was really the first person, I think, to understand this approach to signed areas of triangles and n-gons. And so this is a formula that he wrote in a paper around 1769. And so in the case of the quadrilateral, here we can state it in this way, that if we have 4 points A1, which is x1, y1, A2, which is x2, y2, A3, which is x3, y3, and A4, which is x4, y4, then the signed area of the oriented quadrilateral A1, A2, A3, A4 is given by this expression here. It's 1/2 of x1, y2 minus y1, x2 plus x2, y3 minus y2, x3 plus x3, y4 minus y3, x4 plus x4, y1 minus y4, x1. And each one of these rows is just one of these terms. So this is just S of A1, A2, this is S of A2, A3, this is S of A3, A4, and this is S of A4, A1. With a half, of course. So it's a beautiful extension of the triangle formula. So if we just have 3 points, then the triangle formula that we wrote down is just analogous to this, but we're just going A1, A2, A3, and then back to A1. And the beauty of this formula is that once you understand it, you can see that it's sort of automatic how to generalize it to more than 4 points. All right, we can now talk about the signed area of an arbitrary oriented n-gon. And it's exactly the same story. We just cycle through the various oriented sides, starting from the first, going to the end, and then coming back to the first one. So we've covered a lot of material today. We've done a lot of interesting things. We've really established a good framework for understanding area, the subtlety of area, in particular signed area in the plane. It's crucial that we work with signed area. And we're going to see a lot more examples of the power of this thinking, both in the course materials that are associated with this lecture, okay, which I hope you're all going through, but also in subsequent lectures to come. So there's a lot to learn. I'm Norman Wahlberger. Thanks for listening.